So we're very pleased to have Alex Hauptmann here. He'll be talking about some of his work on the Infomedia project. And actually, I don't know what else he's going to tell us, so why don't we all sit and let Alex take it away. Thank you.
Okay, sure. So what I'm going to be talking about is approaches to video search and classification, and specifically the subtitle is Maximizing the Synergy Between Systems and Humans, because we found that, well, automatically we can't do all that much. So we have to look more towards what people can do. There are really 4 portions to the talk, although not of equal size. One, I'll talk about the Infomedia system very, very briefly. Then I'll talk about one approach to bridge the semantic gap in multimedia, meaning basically trying to help understand what images and what video really stand for. You know, words are nice because we have these clear units, and sort of, you know, a document consists of words, and they sort of relate to what it means. Imagery, you know, you have pixels, but pixels really don't relate to what this image is all about. Then I'll talk about some very serious research, active learning for new concepts. And then I'll conclude with something I call extreme video retrieval, how we really push the humans to the limit utilizing this. So the Infomedia project has been going on for more than a decade now, and we have a system that allows you to do interactive queries on news, multilingual news, and we have a fairly fast and simple interface. We allow map queries where you sort of select a region on the map and say, give me all the news that comes from this area. We have various filtering approaches, and then there's lots of browsing, filtering and summarizing, because we're not delivering the exact content that the user wants, and so we have to give the user a chance to sort of look through it efficiently. And different users might want different things. Some person might be satisfied with just a little bit of text, and other people might want to see the face, or they might want to see a particular action taking place. And so there are different characteristics to queries. So what I'll do, and this is demo time, so maybe it won't work, is give you a quick example of it. So the data I have is from the first quarter of 2005, so it's a year old actually, but it's what I have on the laptop, CNN, Taiwanese television, Chinese television, and Al Jazeera. And since I know what's in the collection, I'll just give a query that's halfway useful. Now, this data has been pre-processed. I have an Oracle database on there that I'm using for the text search. What you see here is one image for each shot. And I can go ahead and play some of these.
أكثر من 140,000 قتيل في زلزال آسيا وتضامن عالمي لإغاثة المنكوبين.
So what we've done here is we've run a speech recognizer across the Arabic, then we've run statistical machine translation across that Arabic transcript. We got the right side there, and then that's more or less aligned. You know, the machine translation, you can't have a word-for-word alignment, so it's sort of a section-for-section alignment. The Arabic is word-for-word aligned with what's in the video, and while you can tell from the translation that this is nowhere near good enough to read and understand, it did give me the right stuff, and there's enough keywords in there to tell you, yeah, this is the right story, and visually you can tell it's the right story based on what's in the video. So this is sort of the very basic Infomedia system. I could give an hour's talk on exactly what the system, what all the features are, but that's not what I was planning to do. I actually gave a talk about this, I think it was around 2002 here, and showed a bunch of the sort of low-level work. It hasn't it's gotten better and it's gotten more varied, but it's sort of, the core is the same. So I'm just going to go on. You have an idea how the Infomedia system works. So yeah, and I should give credit to my colleague Mike Crystal, who is actually the chief interface designer for all of the interface work. So that's not my work, so I'm not spending a lot of time on it. So one of the things that we find is there is this gap. We have video or imagery at the bottom, and there are low-level features that we can extract, sort of color, texture, motion features. We might have some data about the video that was done at capture time. You know, we know what format it is, what frame rate. Maybe we know the title of the video or something, that this is, you know, 6 o'clock, so it must be the news show kind of thing. And then on the right side here, you can't see it very well, it says human annotations. So people might have put a web page around that and said, well, here's some clip of video that's, that shows me falling down or jumping on a trampoline or something. So I might have things that were annotated, and that those annotations can describe what it's about, describe who's in it, whether it's funny or not. It has all different characteristics, so it sort of spans a wide level of things. And then we have the user on the other side, and we don't always know what the user wants and how to get from these low-level kinds of things, they're not words, to what the users want. Users tend to express things in words. Very rarely do they actually express things, I want another picture like this. That, you know, you see a lot of research doing that, but that's rarely what users really want, we find. If they had a picture like that already, then, you know, another one has only small marginal interest. So one of the approaches we've been pursuing is to define a set of concepts that we can reliably recognize based on this low-level or mid-level data, using a number of approaches in a lot of machine learning, but also, you know, some human annotation, some computer vision, some exploitation of the capture data and so forth, and the layout, and use that to find these concepts. And the notion is that, well, you know, so we can do face detection, we can do car detection and so forth, but that doesn't get us very far. But suppose we had 1,000 concepts, and if you think of it as a limited vocabulary of 1,000 words that describe video, maybe that will get us there, or maybe 10,000 words is the right level of granularity, where all of a sudden, if you can use 10,000 words to describe a picture, then all of a sudden you can meaningfully retrieve things that you really are interested in. So that's one direction we're pursuing. I won't really go into more detail than that, but it's an approach. But I'll go on to the next section, which is actually the active learning part, because if you have 1,000 words that can characterize the contents of a video, and users can search that meaningfully, we'll still be missing things, and it's impossible to pre-compute all possible sort of things a user might want from a video. You know, so I want, you know, to see Britney Spears' left big toe. Well, we won't have a classifier that does that for you. We probably won't even have a toe classifier. Maybe Britney Spears will be there, and that sort of thing. But the idea is that if you're interested enough, maybe we can get the user to actually assist the system to build a task-specific concept detector, one of those semantic categories, dynamically to help with retrieval. And so that's the core idea behind what we call ENVI, the Extensible News Video Information Extraction System, that users can create their own concepts. And the idea is you have a user, they there it is. They label some examples. These examples, positive and negative, define a classifier, define training data for a classifier. The classifier builds some models. We take the models, process the archive against with that new classifier, get some new results, give those to the user, and the user can say, well, these things are good, but these are not, and we can keep going that way, iterating over it. So just in case, I was told, I should have one slide in there for active learning. So you have labeled training data. Based on that labeled training data, you classify the active pool. Then you find some informative data which you don't know enough about, but it would really help you if you had that labeled. You get the user to label that, and then you build a new classifier to try and label the rest of the data maybe a little bit better than you could before. And the trick is selecting the right amount of informative data so that the user doesn't have to label everything. And we tend to use SVMs, so we find a hyperplane that separates these, and the things closest to the hyperplane are the ones that we want to label. The data points closest to the hyperplane are the ones that are most informative. At least that's the sort of standard way you could do it. You can play other games as to how to select the most informative items. But anyway, so that's it. There is one additional complication here. We're dealing with multimedia data. And so it's not just a text string that defines this, but for us it's color, texture, edges, audio information, face information, motion information. At a different level, we have the text from speech recognition and video OCR. So we have all these feature sets that all can be used to build a classifier for a particular piece of video. So there are different ways to do that. You can do what's known as early fusion. You can take all these features into one very, very large feature vector and then do your machine learning based on that. But that quickly falls apart if you have small numbers of training data and feature vectors that include thousands of features or maybe even more. Certainly if you use text, you have very, very large feature vectors. Then you can do late fusion, which means build a model for a color detector, build a model for a texture, and so forth for this particular concept, and then take the combination of those the output of those individual uni-modal detectors and combine them, and then have a better detector. But in that process, you've lost a lot of information in between. Plus, that also means you need an additional held out set. And there's some question how to combine the weights for each of the individual classifiers that you're building. So one of the new things we've done in Envy that we build for each feature set, we build a different submodel. Then, and this is in each iteration. And after applying this submodel to the unlabeled data, we take from each of the submodels, we choose k examples which are close to the hyperplane for that particular model. So it's we don't just pick one set of examples, but we pick examples from each different. So we start to vary things from each different submodel, and then we get the user to label these. So in some sense, you're labeling R times k examples. For R submodels, you label k examples. And then so you get the user to annotate them, and then you say, well, now that I have this annotated data, let's assume that's my held out set. I can figure out fusion weights for this data, for this held out set that the user just annotated, and then iterate that way. Does that make sense? Okay, good. So now I'll give some examples, or give some actually hard evidence that this is a good idea, not just intuitively you can nod and say, man, yeah, it seems reasonable. So we tried this over, it's about 70 hours of video, which we subsampled to 52,943 annotated shots. And then there were 20 semantic categories that were labeled on this. They included things like ships, airplanes, outdoors. I forget all the categories now, but a number of those. And we're averaging performance over the 20 topics. So, because for any one topic, it might do really well, but then don't want to leave out the other ones for which it doesn't do well. The features that we actually used for this experiment are HSV color histograms, edge histograms, Gabor features, and faces. Face information includes the size of the face, the location of the face, and how many faces there were, and the confidence in the faces. And then we used a support vector machine with a RBF kernel as our core classifier. So the idea is we trained all this labeled data with multimodality fusion, and we compared a different. So the baseline setting just takes one long vector of all the featured data. The what we call the base active takes does the active learning, so it takes 1,000 randomly annotated shots, and then each iteration you build a new classifier based on these concatenated features. So that's the baseline takes everything with a concatenated vector. The active learning starts doing this in pieces of 1,000 each time. And then the new idea here was to do this multimodality active learning where we start with 1,000, pick 250 sample examples from each of the 4 feature set. And again, that number was just chosen because it divides 1,000 by 4, but you probably can do a better job. And then in each iteration, see what we get. And these are the results. The multi-active gets higher and faster. And you see there's some overfitting here that happens. The baseline concatenated features are just not that great of an idea. And if you do active learning on them, sort of you still don't get all that far. So this baseline is actually the same because we did it on all the data. It was just plotted as a straight line through here. It really happened with 100% of the data. So then we did some upper bound experiments showing what's the best we could do, meaning that if we took all the data and looked at the 4 different feature sets and 16 different combinations of these feature sets, how well could you do? And then we said, well, suppose we took this active learning and start with 1,000 randomly annotated data pieces and take, again, 1,000 new examples. But each time we use the optimal combination for the fused model. And then we find we actually could do, we could get to this optimal performance faster if we did that, if we always knew what the best combination was, which we don't. But then it turns out we would get there faster with 2%, 3% of the data, as opposed to 10% of the data, but we're still getting there with the multi-active approach. So, yeah.
Can you say anything about that overfitting that you're seeing?
Yeah, I think one of the things that happens is that after a couple of iterations, the support vector machine has sort of zeroed in on an area, and even though you're trying to find things close to the margin, they're sort of still within that area, and you're seeing this overfitting to the particular data set that you happen to be looking at closely, that's near the margins between the data set examples that you've looked at, and not way out there somewhere else where the support vector machine thinks it's not a problem, but you don't even ever get to look at it. That's my guess, but
there's actually fairly broad evidence when you're doing active learning with support vector machines using this particular strategy that you come up to you get your optimal performance before the asymptote, and then this thing of reaching a maximum and then decreasing as you get all of the data. You see across a lot of domains.
And then you'll come back up as you reach most of the data, but it'll take a while before you sort of then get to that the line where you have all the data. So comes the moment of great risk. Should I show you this in practice, like what it really looks like? I can try. So it might not work, right? So what do I do here? One of the things that we found with data from not CNN sources, actually Chinese television is not bad, is that especially Taiwanese television is all over the place. And it turns out this person is the anchor here. But see, the CNN anchors sit in a studio, and you can always tell, from the background that this is a studio. This lady here is the anchor person for Taiwanese television, but she has all this junk projected on the back all the time. And the question is, can we now build a classifier that picks out the anchors, not just her in this particular outfit, but the anchors in general in Taiwanese news? So I'm going to give this a try. So the thing, obviously, I have to start with is label some data. I'm going to put this microphone down because I need my hands here. So what I'm going to do is select some of these images. Let's see. And then this seems to be a news story. And then here she is again. Okay, and just for variety, I'll go to another show. So now I have a number of examples. And what the system actually does, it keeps track of what I've looked at and what I didn't select. And those are the negative examples. Now I tell it, go ahead and build me a classifier. And let's call it and obviously it doesn't make sense to classify anything except Taiwanese news with this. So I'm going to just, it does make sense to classify Al Jazeera. I mean, you get something, but you probably don't get good results. So now it fires off this Perl script because, that's a good way to start prototyping. And it's not super efficient, but hopefully it'll finish before I totally run out of things to say. The first thing it does, it scales all the data to be sort of roughly in the same range for all the values. Then it'll try to build a classifier from that, and then it takes the model that it built and applies it to all the data in the database. Now, I should point out that a lot of this research is university-based research. We would not think you could do this over 1 billion images in the Google scale without major rethinking of the whole thing. So my expertise is not at all in the billion image scale. It's much more looking at what we can do sort of on this tens of hours scale as opposed to the billions of images or thousands, hundreds of thousands of hours of video and so forth. So one reason this is also slow is that it's all running on this laptop, right? So everything is local right now. I'm not connected anywhere. All right, I've run out of things to say, and it's not even close to being done. Once it's built the model, then we're within a short period of time, but we're not there right now. Good, model's trained. Now it's taking the data, predicting it. And since we're only predicting over like 10 hours of video, it's not such a huge set. And we've pre-computed all the basic features, the low-level features, so those are there. And now this is the command to update the database. So now it actually is going into Oracle, updating all the database, and it's done. And now I can see what it looks like here. And hopefully it worked. I have no idea. So this is what it thinks it came up with. So this is just a classifier. What it did is actually it did a fairly good job here. This one is, so what I now am going to do is say, well, I want to get this better. First, I clear out the stuff I had before. And then I'll mark this one, because that's not an anchor. Yeah, that's probably an anchor. This one's not. Yeah, it's surprisingly well. Almost too well. Now the active learning won't be impressive. Anyway, I won't get hung up on this. So now I can go back, add this to the no set. If I had seen no good results, I would have added everything to the yes, would have added a lot of things to the yes set. But since I have mostly good results, I append this to the no set for this anchor. The system figures out, oh, we just have to add that to the data. And now I can go off and build another version and so forth. And so I can do this. It does the same thing, and now we wait again and so forth. I don't think I'll spend too much more time. You get the basic idea. And each time it gets a little bit better to the extent that this active learning works. And then, sure enough, if I do this too much, all of a sudden it gets worse, and people in the audience say, oh, that's terrible. So I won't go any further. I'll just leave it at that, especially since it did well in the first round. Let me go back to the talk. OK, I don't have to show you this because I showed this to you live. Oh, yeah, and then I can also then filter results. So I take the results and say, oh, throw out all the things that you think are Taiwanese anchors from this query that I had on whatever, earthquake relief. Just throw out everything that includes the picture of the anchor because I'm not interested in that. So I can filter it. OK. And now I'll get to the final part of my talk, and this is extreme video retrieval. We noticed we've been participating since 2001. We've been participating in annual Trek video evaluations, and they have two tracks. There's sort of the automatic and the interactive track, and this year the best interactive system had a mean average precision of 0.4. Not very well, but this is state of the art. Oh, the other anchor has finished. If you're interested in seeing the results, I can go back to that, but I think you get the idea. By comparison, we also fielded an automatic system, and the performance of this automatic system with the same queries was about 0.1. And what this plots is actually the performance. If you only took the first 10 images, what was your mean average precision? If you took the first 500 images, what was your mean average precision? So it plots mean average precision at various depths. Now you can look at that and say, well, that's not very good. And then we said, well, suppose we had an oracle that could do this better, and for the first 1,000 images, put all the ones that were good in the front and the ones that were not so good in the back. And that would give you, and that's plotted here on this solid black curve. What we can see is that if you had an oracle that looked at 2,000 of the automatic run images, you would do better than what the best interactive system was. And the best interactive system is very much like the classic Infomedia system that I showed you at the beginning. So that's state of the art. So we said, what kind of oracle can we build? We said, we can't build one, but we have a person. So all we need is a person to look at the first 2,000 images, and then we should do better than any system that's currently being fielded. You say, that's silly. Then the question became, how can we make a person quickly look at 2,000 images? There is a time limit to these interactive tasks. of 15 minutes. And so, this is where you start feeling that, oh, this might get to be a challenge, and this is where the extreme part comes in. But first, I'm going to make some comments about the automatic search here over the video, and particularly the combination. Okay, so for this extreme retrieval, we have the automatic retrieval baseline, which just gives the shots in ranked order based on its best guess at this. And then we have two methods of presentation, user-controlled and system-controlled, and I'll show you a demo of that towards the end. The system-controlled is based on something called rapid serial visual presentation, RSVP, that sort of psychologists have experimented with in the past. And then we have the user-controlled presentation, which allows the person to manually push a button and see as many images as they want. You could dynamically resize a page as you're going along. I'll explain that a little more later. But first about the baseline. How did we get this baseline? So the idea is we have all these knowledge sources or individual experts. We have the closed captions or speech transcripts. We have audio features, motion features, colors. And then we have some of these semantic categories like faces, buildings, and so forth that we've tagged our library with. And then we have this query that potentially is text and imagery. In these examples, we never used audio and motion, but we used the images that were provided and the text that was provided. And then, from each of these experts, we get an output. And then the trick is, how do we combine these diverse knowledge sources into a final ranked list? And that's actually one of my students, Rong Yan, is doing his thesis on trying to do that, and I'll give you sort of some of the highlights of that work right now. So what's different is that normally you only have this one path. We have sort of text matching to text. You get some output, and then that's it. Maybe you can think of it as, you have the text and the page rank if you want to look at them as two different sources. Anyway, so you get this final ranked list. And how do you get this ranked list? Well, so what we have a probabilistic model for multimedia retrieval, and the basic model is logistic regression in that what's the probability that document meaning a video shot is relevant to a particular query, and we estimate this as the weighted sum of the individual experts. The relevance of the individual experts gives us the total experts. And this is logistic regression, so it fits in here. And the idea is you want to learn these combination weights from past results. Well, the problem is you can't learn it from every query. You don't have a history, what's the correct result for this query on some other collection, which would give you a sense of what the weights should be. The other thing we had to do is logistic regression is designed for classification, sort of a binary thing. But a binary classification has a bias towards irrelevant document in the sense that if 99.99% of your collection is irrelevant, then this logistic regressions will say, well, my best guess is just call everything irrelevant and I'll do fairly well according to the logistic regression. You don't want to do that. So we have adapted this ranking logistic regression where the basic logistic regression term here gets modified by a sort of in what's not relevant, and you take the difference of them. So you're looking at maximizing the prediction gap between the positive and negative examples. And you can sort of see it as a lower bound on average precision. And then since that's actually fairly expensive, we can do some approximations to get this to be same complexity as logistic regression as opposed to being n squared. And so one of the other things that we can do here is, so if you take all the past queries and say, well, on average for all the queries, what was the text weight, what was the image weight, and so forth, you get this. You get some sort of uniform weighting over all the queries. And it turns out that's not very good because queries are all over the place. If you're looking for a person, you would emphasize facial feature and maybe a person classifier. If you're looking for oceans, you would say, well, I don't want a face to be big in this, because then it's unlikely to be an ocean thing. So different queries have different characteristics. So this isn't very good. What we really want is we have different query classes, and we map each query into one query class, and then for this query class, we have a set of weights, and we can learn these based on examples of these query classes. That's feasible because we only have 5 query classes, so it's doable. And then for a new query, we can say, oh, it's most like query 1, or it's like a mixture of query class 1 and 2, and so therefore we have the weights be a mixture of those two, and we get results. I'm still doing okay. So the whole idea is here we have this additional term in the logistic regression that introduces the query types or the query classes that we have here. And so if you remember, this was the stuff we had before, and now we're just introducing this additional class that says, for this particular query class, we use these sets of weights. And in practice, we've used 5 different query classes: named person, named object, general object, and scene and sports queries. There's also some work that you can automatically find these query classes for which query classes, which queries tend to cluster together to form a class on their own. And then the other thing is, what about these semantic concepts that we don't really have good query classes for? So, for example, if we have a boat ship query, then we might say, well, you want text, you don't want faces. The imagery is important, meaning if you have an image example, then give it this weight. But we don't know how to combine that with outdoors and ocean, because we don't really know how boat ship, that specific query, or even the query class of general object, relates to outdoors and ocean. And so for that, Rong has adapted something called Probabilistic Local Context Analysis, which he borrowed from the text world, where you take these documents and basically look at the top few, do the equivalent of pseudo-relevance feedback, assume that they are right, and then feed that back. But because this is multimedia, you can't assume too much about the top things being right, so you have to be very, very cautious in feeding things back, because you can very easily, if the top 10 things are bad and you feed back from that, all of a sudden you're off on the deep end. So you have to be very, very conservative on these things. But you can control that. And so now we have, so this is the term we had before, for each expert, we look at the relevance, the weighted relevance. And now we have this additional term here that says, for this specific query, can we also estimate the relevance of a particular source to this, for this particular query based on this relevance feedback? And it gets more expensive, but you can actually do that. And so the bottom line is, does this work? How well does it work? So we looked at the baseline automatic system result, and then we applied these retrieval experts and 15 semantic features, face, anchor, commercial, studio, graphics, and so forth. And then we used the relevance-based probabilistic retrieval model, basic model, and then this the model with this query analysis. And we present the shots. And actually, this is the wrong result slide. The baseline is here, is one of these. And if you put all this stuff together, you get significantly better. This is, again, the TrekVid results. Turns out these guys here cheated by using Google external information about news that helped them get better query expansion. So, okay. So this is just an aside, really, to lead up to this extreme retrieval idea. So let me first give you a talk about this system-controlled presentation, RSVP, Rapid Serial Visual Presentation. The idea is you try to minimize eye movement. You know, don't do anything don't make the user do anything that's not relevant to the task. So minimize eye movement. All the images come up in the same location. You maximize information transfer, meaning you put up a lot of images very fast. In theory, you can do up to 10 images per second if you're bringing up a single image. And then we've played around with 1 or 2 images per page, because it turns out you have 2 eyes, right? So you can look at 2 images at the same time. And so you bring up the images, and then after, say, 300 milliseconds, it switches to the next one, and so on. And if one of them is correct, then you hit either the left or the right button, and off you go. And it marks that one as relevant. And then you find that in the beginning, it's quite hard to do this. But then after 30 seconds or so, your brain adjusts to this rhythm, and you say, okay, I can do this. And then we have a button say, go a little faster. So at the end, you can go quite fast, sort of in the 200 to 300 millisecond range per image or per page. And especially if there are few relevant images, sort of, you can quickly eliminate them. It turns out not every query is the same. So some queries you need to look more carefully, and they're slower. And others, say, is this soccer? Well, you can tell that pretty quickly. Can you see a left hand? Well, you have to look more carefully. So it's a much harder kind of task, and so it takes you cognitively longer to do this. What also happens is you're not always fast enough. These things come whizzing at you at a fairly good clip. And so sometimes as you're pushing the button, it's paging to the next page. So you actually have to mark the previous one as well as the current one, because you don't know which one did the user mean. And that means at the end, you actually have to have a little phase of cleaning up, because you're not sure which one was the one you really wanted. So that's the verification step at the end. And I think I'm going to try that now. Let me see if I can do this. Okay, so we need shots of Omar Karami, the former Prime Minister of Lebanon. Actually, let me find something that everybody knows about. Tony Blair. I'm going to just load 1,500 images. So this is the ranked output of the automated results. So right now it's loading them, and since I have all this other stuff, I still have the Infomedia system up and the Oracle database up. It takes longer. But this is really pretty simple, because all I'm doing is loading up a bunch of images into memory. I mean, they have to be in memory because you want to do this rapidly. And then I think the configuration right now is such that it's 4 by 4, so I can use 4 keys, 4 fingers, and say which one is there. And I'm also going to have to be quiet, because once this starts, it's not like I can do this and talk at the same time. Like, my brain cycles are not fast enough for that. But it's amazing how much you can adapt to it. So I mean, I'm just going to do like a couple minutes worth, no, a couple seconds worth of this once it loads. I did start late, so I'm almost done though. Okay, so it hasn't started yet, but so we see Tony Blair is in the bottom right here, right? So let me start this, and then you can just watch the images flip by, because it's going to go pretty fast. So I mark this one as green, and we start. Okay, this is way too, so I need to go slower. Nope. So you get the idea, right? And you can then speed it up to the point where if you're going, if you're doing really good, you can, go faster and faster as you're doing this. And this is extreme in the sense, I think I'll just stop here. It's extreme in the sense that you don't want the phone to be ringing, you don't want anybody to come to your door. And in fact, I actually did this too, and my students did it, several students, and 2 undergraduates did it. And when you're doing this, you actually, at some point, you don't want to blink anymore, because blinking takes so much time. So you find yourself, trying to keep your eye open and not to blink while you're doing this. So this is on the extreme side of things. Let me go back to the talk. Okay. So that's what I just showed you. And so on the slightly less extreme side is when you control the paging manually when you get to next image. And so you have a button that says next page, next page. And what we found very effective is that you vary the number of images on a page. So initially there's only 2, and you can say left, right. And then as you get less dense in the relevance things, then it makes sense to have 4x4, because you can eliminate them fairly fast, and you only have to hit one of the 4 buttons. And then 3x3, 2x2, 3x3, up to 4x4. We didn't go further than that. And you have a chording keyboard, so you can hit 2 or 3 keys at the same time. And again, there was, since you do make mistakes when you're pushing yourself to the limit, there was this final verification step. So the question is, how well did it do? And here are the results. So the in this TrekVid 05 thing, so the classic Infomedia system was here. There was another system from a former student of mine, actually, that did a little bit better. This was the manual browsing with resizing of pages, and this was the just single image flashing at you fairly fast. Turns out, by the way, another thing is you do start to dream about these images at the end of the day, because they come up so fast and your brain just can't process them, so they sort of stick around with you for a while. It's quite interesting. Anyway, the very positive news, this very dummy approach, as one of my students called it, was statistically comparable to anything else. So once you have this halfway reasonable baseline, this is good. Now, do I really think people want to do this? If you've ever heard of the ESP game, people play that game for, I think they've put a limit on it for 14 hours, because then they sort of say, you've got to take a break. And this is just another version of this type of a game, right? And if you've played video games, the undergraduates who play video games a lot, they do this very well. I have a much harder time. So, but the whole point is we want to do active learning here. And then we actually have some experiments that show if you can do this, so you're getting feedback while the user's doing this, whether you do it with manual paging or the extreme system-based paging. The system can learn, and if it can learn fast enough, currently we're not fast enough, as you saw, if the system can learn what's relevant and what weighting should be used, then it can rearrange the rest of the imagery to give you more and more of the relevant things quicker, and then you can actually do even better than what we saw from the earlier baselines, because you can rearrange the whole collection each time and do fairly well. So I don't think this extreme retrieval, the way I showed you, is ready for a product for somebody to buy, but I do think in conjunction with active learning, it is one way to sort of make retrieval of images and video better than it used to be. So the idea is we exploit the human's ability to do what they're good at, which is identify whether this is something they want or not very quickly, visually, and the computer's ability to learn and rearrange things based on the examples. That's it. I'm done. Thank you.